Hello, everybody. So continuing with our parade of techniques for integration, we're going to do something called, we're going to use something called partial fraction decomposition to integrate rational functions. So for example, the integral we see here, this is a rational function, right? Rational functions are just quotients of polynomials. So we've got here x minus 7 over x squared minus 1. This is a difficult integral to do as written. There might be a few ways to get at this, but one way is partial fractions. So we're going to go through the method, but I want to motivate it because it's kind of a complicated method. So I want us to see where this is going, why we might do it. The reason, so we don't see maybe an obvious way to do this integral. However, using the method of partial fractions, we will find that we can rewrite this rational function as the sum of two fractions. Okay, and you'll be able to quickly see if you find a common denominator that you can put this back together and get exactly what I've written here. And so by substituting this new expression for the function we started with, we still have two rational functions, but they're much simpler than the one we started with. We can use our rules of integration to turn this into two integrals or antiderivatives. And both of these are relatively straightforward. Okay, so of course I skipped the big part, which was how did I know to use these two functions? And that's what the goal is here. Is how can we break down these kinds of rational functions into, decompose them into these partial fractions. Okay, so let's now dig into the meat of this. There's going to be this video is going to mostly focus on the idea. I suspect it won't make much sense until we get into the next video and we run through a couple of examples. So in this video, I'm going to focus on just setting us up with, we're going to develop some rules for doing this, but then in the next video, we'll actually follow through with using those. I think this one will be long enough on its own. So here's the idea, right? We want to integrate a rational function. Let's call it f of x, and we can give it a rational function is always going to be of this form, where p and q are polynomials, right? Sums of powers, linear combinations of powers of our variable. So we've got the quotient of two polynomials. We're going to assume that the degree of p is less than the degree of q. Okay, so that means remember the degree of the polynomial is the power, the highest power that appears, right? So a quadratic x squared plus 5x minus 2 is degree 2 because of that x squared. 2x minus 1 is a degree 1, a linear function. If they're ever not, we can always convert to to this situation in the following way. If not, if p is higher degree than q, then what we can do is use polynomial long division to rewrite this as in the following way, right? Where this is a polynomial, and now the degree of r is less than the degree of q. Okay, so if we ever are in a situation where this is not true, we have to first go through the process of polynomial long division, which I am not going to cover in this video. That is something I assume we have familiarity with, though they're easy to find review videos on that if you want to. But what it means is, since we can always do this, then we know how to integrate polynomials, and what we have left is a rational function where the degree of the numerator is less than the degree of the denominator. So we can always get ourselves into this position. That's why this assumption here is safe. We need to deal with what happens once we're in this position. How do we make sense of this rational function? Okay. So what we want to try to do, we want to take P of x over Q of x and rewrite it as a sum of several functions, right? How many, it's hard to say, right? In the case I did up here, right? These F1, F2 up to F sub k are like these. In this case, I had an F1 and an F2 that I'm adding together, right? And we want, and these F's are going to be more rational functions, just like we had up here, but they're going to be simpler, okay? So how do we find them? Well, one clue we're going to have is going to come from real numbers. So let's just do a little bit of a reminder on the side. For instance, if I had the fraction 13 over 8, right? It has factors, 3 factors of 2 in it, right? Well, with a little bit of trial and error, you can find out that this is 1/2 plus 3/4 plus 3/8, right? So notice on the right, we have a fraction with a power of 2, a fraction with a power of 2 squared, and a fraction with a power of 2 cubed, okay? So because this side had a 2 cubed in it, we ended up having a 2 squared, and a 2 cubed in the denominator, right? So think about the process of finding common denominators. These 3 things here these 3 denominators on the right have a common denominator of 8, and that's how we ended up with what's on the left. But notice something else. If we have 7/8, for instance, this can be just written as 1/2 plus 3/8. We have a factor of 2 and a factor of 2 cubed, and this side has a factor of 2 cubed. So we have, again, the common denominator is 8, even though we don't have the same situation as above. So this is one big idea in all of this, that if we have a factor in our, this is like the rational function we're starting with. These are like the F's. We're going to write it as that if whatever factors Q has is going to determine the factors over here. Or for instance, let's do one more. If I had something like 7/12, this could be 1/3 plus 1/4, right? This over here has factors of 3 and 4 because this over here had factors of 3 and 4. On the other hand, if I had 13/12, I have 1/3 plus 1/4 plus 1/2. I still have a common factor of 12. I have a 3 and I'll write it this time as a 2 squared, because on this side I had a 3, I had a 2 squared, and I had a 3 times 2. I don't need to repeat this 2. It shows up here, and we end up with just a 2 squared on this side, okay? So there's a lot of the lessons in factoring and getting common denominators from fractions that we're going to be using here, okay? So let's go back to polynomials. So the big takeaway from this is we're going to determine the f sub i's based on the factors of Q, the denominator, right? Just like the things on the right over here were, the denominators were determined by the factors of the denominator on the left. A useful fact is that a polynomial can always be factored into linear and irreducible quadratic factors, okay? So linear factors, lines, right? 2x plus 7, 3x minus 1. Irreducible quadratics, that means we have quadratic functions, x squared plus 2x minus 7, but they don't have any real roots, right? In other words, if you think of your polynomial, your quadratic is looking this way, b squared minus 4ac is negative, right? This is when if you use the quadratic equation to find the roots, you get a negative under the square root, which means the only roots it has are imaginary numbers, complex numbers, which are, of course, very important. And the imaginary is a poor term for it, but it's just what has stuck. But it's not what we're going to deal with. So we're going to talk about irreducible quadratics, meaning they have no real roots, only complex roots. All right. So there are going to be two rules that we will go through in the next videos for determining what we write on the right side, right? Remember, we're going to be starting with p of x over q of x, and we're going to try to write this list of simpler fractions based on the factors of q. And our rules are this. If q has a factor of ax plus b to the n, include, meaning in this list, we're going to include f sub i's of the following form. So a1 is a constant over ax plus b, plus a2, another constant, over ax plus b squared, and you keep going until you get to a sub n over ax plus b to the n, okay? So let's just look for a second at what I'm saying. If q, our polynomial in the denominator, has a linear factor, ax plus b, where a and b are constants, that's a linear factor, 2x minus 13, right? To a power. Then for each power, we include, right, there's a linear power. So let's, for instance, say n is 7. We would have ax plus b squared, ax plus b cubed, on up to ax plus b to the 7th in the denominators. And in the numerator, we would have constants. Each one would have its own constant, right? This is very related to what we were just looking at over here when we had 13/8. There's a 2 cubed. We see that there's a factor of 2, a factor of 2 squared, and a factor of 2 cubed. We're doing the same thing with our linear factors here. If there's a linear factor cubed, we need the linear factor by itself, the linear factor squared, and the linear factor cubed, right? Notice we also saw examples where sometimes, even though we had 2 cubed, we didn't have all of those factors. We skipped over, for instance, in this 7/8 example, there's no 2 squared factor. That's fine. We might skip over some here as well. That will just show up because these constants on top can turn out to be 0, but we have to investigate to find out whether they are, okay? All right, and now if q has an irreducible quadratic factor, ax squared plus bx plus c, remember this means, oops, let's get my eraser, let's make this look nice, to some power, we'll call it m, where b squared minus 4ac is less than 0, that just means it's irreducible. So if that's one of the factors of q, if that's one of the factors in our denominator, then we will include the exact same idea. We will have, well, similar idea. We will have factors that look like, or terms on the right-hand side that look like this. a1x plus b1 over ax squared plus bx plus c, plus a2x plus b2 over ax squared plus bx plus c squared, on up to a sub m x plus b sub m over ax squared plus bx plus c to the m. Okay, so we've done the same thing. We've done the same thing that we did with the linear factors, where we included, if it's to the mth power, we include that quadratic factor to the first, that quadratic factor to the second, on up to the mth power. And in the numerator, instead of having constants, we have a linear polynomial, right? So in the first case where we had linear factors in the denominator, we had constant factors in the numerator. When we have quadratic factors in the denominator, we have linear factors in the numerator. So the degree goes down by 1 as we go up. And again, some of these could turn out, some of these constants, the A1, B1, A2, B2, could turn out to be 0. We don't know ahead of time. And so you'll often find out that you've written down more than you need. But there's really there's not a good way to tell other than the process we're going to go through in the next videos. Okay? So I suspect in this video, it's not very obvious exactly what I mean. So I'm going to start the next one from here, but these can take a while, and I think the whole video will be too long. This is probably a good moment to take a pause. And in the next couple, we'll do examples of the different kinds of problems we can see. Okay, I will see you in the next one. Thanks, everybody.